mai nay pui dan alo pi e ma lo a kon hit san ka lun nang zal a hi pa kai ka ki pa ka gel pa lo san ge nay pui e pa ka nang zal a hi pa kai ka ki pa nang zal a hi hit san kan hun the na phat na ho hi ka gel zi te a lo pi dan tim thu a say zo hi lo o pa kai i pi ham ka bolu pa nang zal a hi hit san kan hun the na phat na ho hi ka gel zi te a lo pi dan tim thu a say zo hi lo nu pha hi lo mai lam ka hin ko zalin ma nei pui lung pa kai na hat na zalin nang zal a hi pa kai ka ki pa nang zal a hi hit san kan hun the na phat na ho hi ka gel zi te say zo hi lo kha ve kom le thom hau na mun na kat ve kom le gen thei na mun na galam nei pui gal kai zi nang zal a hi pa kai ka ki pa nang zal a hi hit san kan hun the na phat na ho hi ka gel zi te a lo pi dan tim thu a say zo hi lo ki pa nang zal a hi hit san kan hun the na phat na ho hi ka gel zi te a lo pi dan tim thu a say zo hi lo
comprises of 5 chapters. The first chapter is the introduction of liquid crystals, and in the second chapter we'll look at the tuning of phenol-based derivatives for aggregation-induced emission and liquid crystallinity in the same module. And third, we'll look at the effect of peripherals like chain density.
Your slides are not visible.
Please check whether it's edible.
Yes.
share the screen. Close this one. Go to the first slide. So is it visible now?
Yeah, I think there will be time lag.
Time lag is there. Go to first slide.
Also, slowly.
That's
one side to one.
Okay.
Dongle disconnected. Dongle connected.
You can come here.
Can you see now?
Sir, is it visible now?
No, not yet.
Talk of the thing and they can share.
You can share the screen.
Stop. Can you stop presenting? I think it's
In the same molecule. And in the third chapter, we look at the effect of variable gene density and positioning of the assembly of naturally pyrazinophenoxine derivatives. And the fourth chapter will increase the core and we design, synthesize and characterize novel benzopenoxine derivatives. And in the fifth chapter, we'll look at the effect of oxidizing moiety on the self-assembly of phenoxine derivatives. So coming to liquid crystal, as we all know, it is a state of matter that is intermediate between the solid state and the liquid state. So they have the property of both liquid and the solid. So coming a brief history of the liquid crystal, it was first observed by a botanist while studying cholesterol benzoate derivative. So on heating the cholesterol benzoate derivative, he observed that the molecule, it started to form a cloudy liquid at around 144 degrees Celsius, but on further heating at around 178 degrees Celsius, it formed a clear liquid. So this cloudy state of intermediate was further studied by German physicist Otto Lehmann, who later coined liquid crystal. So after 1904, several liquid crystal compounds have been reported, but it was only in 1977 when an Indian scientist, Chandra Sekhar, discovered the viscotic liquid crystals. So the liquid crystal mesophase can be characterized primarily by BOM, that is the polarizing optical microscopy, where the birefringent texture of the mesophase can be observed, and the phase transition and associated enthalpy change can be observed from the DSC curve obtained from differential scan calorimeter, and the symmetry of the mesophase can be confirmed by temperature-dependent X-ray studies. So liquid crystals can be broadly classified into thermotropic or diatropic, depending on the stimuli causing it, and my work is mainly focused on viscotic liquid crystals. So viscotic liquid crystals, they have rigid core, and on the periphery it can be modified to form liquid crystals. So these viscotic liquid molecules, they stack one above another to form columns, and depending on the arrangement of the different columns, they can form different arrangement, like they can be rectangular mesophase or columnar mesophase or etc. And because of the solution processability of the liquid crystalline molecules and their alignment, they form various applications like in photovoltaic device, field effect electron transistors, OLEDs, etc. So these are some of the viscotic liquid crystals. My thesis is primarily on this phenoxylene-based derivatives. So as we know, these shape molecules, when they stack because in higher concentration, they tend to undergo aggregation caused quenching. So to overcome the quenching, here we have chosen phenoxylene core, which is versatile core. It can support self-ordered self-assembly. It can support self-assembly, and also the photophysical property can be tuned. So here we have proposed tuning of phenoxylene-based molecules to show liquid crystallinity and aggregation, even though they are usually contrasting properties. So AIE, that is aggregation index emission, it was first observed in this silol derivative. So AIE is usually shown by molecules which have where the pi intermolecular interactions are strongly hampered. Here they have inherently twisted core, because of which they show AIE. And here the electron withdrawing, substitution of electron withdrawing group and donating group to the phenyl groups which are attached to the pyruvyl ring resulted in AIE. And here this phenoxylin derivative which have diamine phenyl groups showed it did not show AIE but reduced the aggregation cost quantity. So these are some examples of columnar molecules showing columnar isophase with wide temperature range. I would like to point out that these molecules have ester and amide linkage. And phenoxylin derivatives have been reported. They are versatile core. They can give rise to different shapes and conformers, leading them to different self-assemblies. So for the first work, we have designed these molecules where we have the phenoxylin core, phenoxylin core with diamine phenyl groups, and then ester linkage. In the first three molecules, the phenoxylin molecule, in the first three molecules, the first three molecules vary by the substitutions at position 6 and 7 of the phenoxylin core, and in the last four molecules, we have the alkoxy chains at the position 6 and 7, and we vary the number and position of the alkoxy chains. Coming to the synthesis, starting with LSO by Friedel-Crafts acylation, I formed this diketo, and the methoxy was demethylated to hydroxy group, and then the hydroxy was reacted with the acid chloride to form the linkage. And this diketo was coupled with different diamine, giving rise to the three target molecules. And for the synthesis of the QER series, different diketo intermediates with different alkoxy number and varying in position and number was coupled with the with alkoxy diamine synthesized by this route. So finally, after coupling together four target molecules, where we have the alkoxy chain at the position 6 and 7. Coming to the mesophase characterization, in case of QE series, where we have unsubstituted, cyano-substituted, and fluorine substituted, we did not observe any birefringence texture, signifying that it does not show crystalline behavior. And for QER2, the 6 and 7 positions have alkoxy, and the two alkoxy at this position did not show any characteristic feature of mesophase. But for QER3, we have for QER3, two alkoxy chains are present at this position. It was found to have, under Lhouvum, it had crystalline texture, which was evident from the DSC curve as well. And for QER4, it had only methoxy chain at this position, and it formed this type of texture, and DSC suggested that it could be because of slow crystallization. So, but for QER1, where three alkoxy chains are present, this birefringence texture was observed, and from DSC, we can see that the isotopic temperature was around 34 degrees Celsius, and in the DSC cooling curve, the transition from the isotopic to the mesophase state was not that clear. However, from the XRD studies, we observed an intense peak corresponding to Miller index 10, and two peaks in the wide-angle region corresponding to the peripheral alkyl chain and the force timing. So this XRD data supports columnar hexagonal mesophase with Bladder's parameter 33.2 angstrom and packing distance of packing distance of 3.9 angstrom, and the number of molecules present per unit cell was found to be 160. So out of the 7 molecules, only 1 molecule was found to exhibit liquid crystalline behavior, and from thermogravity analysis, all the derivatives were found to have high 5% decomposition rate, all above 300. Coming to the photophysical properties, the derivatives are similar, more or less similar absorption and emission spectra. In case of the QV state, the QVCEN and QVR3 show the red shift. So from the absorption rate of the absorption spectra, the optical band gap were calculated and found the QVCN was found to have the lowest band gap. In designing this molecule, we expected the molecules to show aggregation-induced emission because of the slight twisting possible because of the dangling phenyl groups. So we have maintained same concentration for the compound and varied the fraction of water in pH water mixture. So for QV series, on increasing the water fraction, the emission intensity increased to maximum at 80 degrees Celsius, 80% water fraction. And for QECN, this QE series, even though the emission intensity increased the effort 80%, the observed emission enhancement in emission was not that obvious from when observed under the UV light. However, in case of QVR series, when the alkoxy chains were substituted at position 6 and 7, they showed with increase in water fraction, the emission intensity was higher at 70%, slightly reduced at 80%, and reduced further at 90%. So for this QVR series, the observed emission intensity was also visible with the naked eye. And from the we have the optical band gap calculated from the red edge of the absorption spectra, and from cyclic voltammetric studies, we obtained the reduction onset value, and from there we calculated the LUMO values and HOMO values. So coming to the theoretical studies, for QEs, for this QE series, the QEH and QEF had similar HOMO and LUMO distribution, but for QECN, probably because of the presence of strong electron withdrawing group, the HOMO was localized mainly on one of the terminal phenyl rings. And for QER series, all the derivatives showed similar HOMO and LUMO distribution. So this is about the characterization of the all the molecules where all the molecules showed aggregation-induced emission, and one molecule QPR1 showed liquid crystalline behavior. So the liquid crystalline behavior had a theoretical HOMO value of minus 5.67 electron volt. So this was used further for this was studied using SCLC method, where the current density, where the whole mobility of the material was analyzed. So for this method, the ITO, the Indian Inox uses the anode, and the compound was sandwiched between the anode, that is the ITO, and the electrode, that is gold. So in this JV plot, current density versus voltage plot, we obtain a semi-log graph, and using Morgan equation, this whole mobility of the compound was found to be in the order of 10 to the minus 5. So even though this compound showed narrow mesophase width, we could calculate it showed columnar mesophase, where we calculated the whole mobility to be this value. So in conclusion, all derivatives showed aggregation-induced emission, out of which the QVR also showed liquid crystalline behavior. And so we can say that this targeted molecular design enables the integration of the contrasting behavior of aggregation-induced emission and liquid crystallinity. So in this chapter, we succeeded in achieving aggregation-induced emission and liquid crystallinity in the same molecule. However, the low mobility that we obtained was not up to the mark. So in the next chapter, we introduced this pyrazino-phenoxylene core. So in this chapter, we look at the effect of peripheral chain density and positioning on the self-assembly of the pyrazino-phenoxylene derivative. So with the incorporation of this pyrazino-phenoxylene moiety core, we expect the mesophase width to increase and also the hole mobility to increase. So here are some of the already reported pyrazino-phenoxylene core. Here compound 1 and 4 was reported to show liquid crystalline behavior, whereas 2 and 3 did not. So attachment of this alkoxy chain in compound 1 and 4 could be important in bringing about liquid crystalline behavior in these compounds. And previous work from our group, where pyrazino-phenoxylene core were synthesized with different chain length compound. The derivatives with chain length 8, 10, and 12 were liquid crystalline. Out of this, the one with chain length 10 was used to realize OLED, and the charge carrier mobility of that molecule was found to be in the order of 10 to the power -3. And when the phenyl group was replaced with carbazole moiety and the terminal chains were branch chain, it was found to be non-crystalline, non-liquid crystalline. So for this chapter, we have introduced, we have proposed these target molecules, where we have the pyrazino-phenoxylene core with the remaining phenyl groups and then ester linkage, but we vary the position and number of the terminal alkoxy chains. So this again is a synthesis. It's similar to the second chapter, but in the final step we use the hexagonal to get the 3 target molecules. So we basically use different diketo coupled with this hexagonal to form the target molecules. So coming to the mesophase characterization, PQE1 under BOM showed by reference in texture, which is very clear from the BOM image. And from PSC, we can see the phase transition from mesophase to isotropic temperature at isotropic state at around 98 degrees Celsius. And on cooling, the transition from isotropic state to the mesophase state was observed at around 94 degrees Celsius. And from XRT was conducted at 28 degrees Celsius, confirming the columnar mesophase of the compound. So data, we could obtain the gas parameter 43.4 degree angstrom and packing distance of 4.4 angstrom. And this molecule, at 28 degrees Celsius was found to have number of molecules per unit cell to be 2. So that means in a core there are 2 molecules forming 1 core. However, for PQE2 and PQE3, these both have 2 alkoxy chains on the 1 phenyl group, but very in position, the BOM suggested a crystalline protection. So for PQE2, even though the DSC did not show a clear transition for isotropic state to crystalline state, the BOM observed was not shareable, suggesting that it is crystalline. And for PQE3, the transition from isotropic state to the crystalline state is very obvious, clearly marked by this sharp peak. So out of the 3 derivatives, 1 derivative where 3 alkoxy chains are present was found to exhibit columnar mesophase, and all the 3 derivatives showed high thermal stability with 95% decomposition all above 300 degrees. So since these molecules have similar core and structure, but they differ only in the terminal alkoxy chain, they have similar absorption and emission spectra. And from the optical band gap obtained from the absorption, it was found that all 3 derivatives showed similar, same optical band gap values. And from the cyclic volcanic study, the HOMO and the LUMO and the HOMO value calculated was found. It was found that in PQE1, the LUMO and the HOMO were slightly lower than those of PQE2 and PQE3. And in theoretical, the since all the derivatives again are similar, both the LOMO and the HOMO distribution were similar, with PQE1 having HOMO of minus 5.80 KLPD. So this molecule was also studied by SLC method to derive the whole mobility. And here ITO combined with P or PSS was used at the end and both as the cathode. So from the whole mobility extracted was found to be in the order of 10 to the power minus 4. So there is we can observe an improvement from the phenoxylene 4 so the whole mobility increased markedly from 10 to the power minus 6 in the previous chapter to 10 to the power minus 4 in the pyrazine phenoxylene 4. So in this chapter, we introduced pyrazine phenoxylene 4 where we varied the alkoxy chain and one derivative PQE1 structural and hexagonal phase with a certain temperature. And we could also increase the mesophase with signifying that this pyrazine phenoxylene 4 can correlate with cause the increase of mesophase weight and also increase the molecular mobility. And so this we can say that the alkoxy positioning and the alkoxy density helps in stabilizing the mesophase. So overall, coming from the last chapter to this chapter, we can observe mesophase increase, mesophase range increment, and whole mobility improve. And for the fourth chapter, we have the design, synthesis, and characterization of novel benzotriphenoxylene 4 based research. So for this chapter, we work on this benzotriphenoxylene 4. So as we know, for charge transport, the charge transport depends on the balance of the molecular structure and how the molecules stack to form column. So even though there are many already reported big pores which have liquid crystalline derivatives such as triphenylene or hexazotriphenylene or hexabenzoprene, etc. In here we have this triphenylene derivatives where the periphery is functionalized with sp group and then the linkage in the long chain. And then here we have introduction of amine group. And for this hexazotriphenylene derivatives, here in this derivative they have introduced alkoxy and cyano alternately, which became designed for making organic material. And this hexazotriphenylene, even though it's a big pore, with the modification in periphery, introduction of alkoxy chain and oligo chain, even though it's a big pore, liquid crystalline property could be observed. And then coming to the benzotriphenoxylene pore, this pore is similar to the previous previous pore, but differs by the nitrogen atoms. So this benzotriphenoxylene pore, these derivatives have been reported where they are either crystalline or they form 2D polymer or COF. So we believe that this benzotriphenoxylene would be a good, it could be used for synthesis of liquid crystalline because of its shape, where we expected it to show higher charge mobility and we think even though it's a bit with the introduction of peripheral chains could give rise to liquid crystallinity. We have proposed these target molecules where we have benzotriphenoxylene core and the phenyl groups, and then ester linkage in the BQE molecule, and in BQA instead of the ester we have the amide. So we will, it is envisioned that because of the presence of amide in this BQA, there will be hydrogen bonding, which will lead to further increase in mesophase range. So this is the synthesis of the BQE molecule. So in this article is coupled with triphenylene hexaamine derivative compound, to give this BQA molecule. For the BQA molecule, starting with methyl formyl benzoate, by benzoin condensation, we form this benzoin and then oxidized to give benzene, and then the ester group of this benzene was hydrolyzed to acid, and then the acid was converted to acid chloride, which was reacted with the amine formed by this synthetic graph to form this amide aldehyde. And then the amide aldehyde was coupled with this triethylene propionate to give the BQA compound. So we expected the BQA molecule to exhibit hydrogen bonding. So this is the proton NMR, temperature dependent proton NMR. So this at 35 degrees Celsius and 45 degrees Celsius, the peak corresponding to the amide proton was shifted to lower chemical strength value. So in this proof that there is presence of hydrogen bonding. So with increasing temperature, the hydrogen bond weakens and the amide proton is less deshielded, so the chemical should decrease. And also the IR spectra of BQA and BQE are captured. For BQA, the amide stretching frequency was observed at 3281 and carbon stretching frequency at 1649. So these values are consistent with the NH stretching and carbon stretching of hydrogen bonded molecules, and also compared to the non-hydrogen bonded amide, these values are lesser. So this further confirms the presence of hydrogen bonding in BQA molecule. And also in BQE molecule, which did not have hydrogen bonding, which did not have NH amide bonds, the carbon stretching frequency was observed at 1733. So the carbon stretching frequency observed for BQA molecule was lesser. So this further proves the presence of hydrogen bonding in BQA. Coming to the mesophase characterization for the ester derivative, this texture was observed under PO, and from DAC we can see a transition from mesophase to isotopic temperature at around 185 degrees, and transition from the isotopic to the mesophase at around 80 degrees Celsius, and from XRD at 28 degrees Celsius. The Miller indices, these Miller indices correspond to rectangular columnar rectangular mesophase with the lattice parameter 41.7 and 38.5, and the binding distance to be 4.3 angstrom. And for BQA molecule, this texture, and because of the amide bond, again it has a high clearing point around 317 degrees, and on cooling it transforms to isotopic mesophase state. And this was confirmed with temperature dependent XRD. This is XRD at 30 degrees Celsius, which confirmed the columnar hexagonal mesophase of the compound with the lattice parameter 45.8 and core packing distance 4.4 angstrom. So these both BQA and BQE molecules, they were found to have a number of unit cells, the number of molecules per unit cell to be 1. So this probably because of the shape of the molecules, where one molecule gives rise to one disc. So among both the derivatives show columnar mesophase, one with rectangular phase and another with hexagonal phase. And from thermogrammetric analysis, BQA, the amide compound, was shown to have 5% decomposition at 281 degrees, and for BQE it was at 345. And because of the difference in linkage of the derivatives, the BQE and BQA showed slightly different absorption and emission behavior. In case of BQE, these two at 290 and 347, they were of almost same intensity, whereas in BQA molecule, this 348 was higher than 290 peak. And also, the emission peak was wider in case of BQA, probably because of the accumulation. And in thin state, a big reaction was observed in case of BQA. So visually, it was clear that this BQA was more fluorescent than BQA. So we start dealing with the absolute quantum yield of the BQE and BQA derivative. And in solutions, the BQE was found to have 55%, whereas BQA, even in solution state, only had 0.38%. So from the optical, from the absorption spectra, this band gap was calculated to be 2.77 and 2.75, and from the cyclic voltammetric study, the LUMO and HOMO were calculated, and BQE derivative was found to have slightly lesser values than BQA of band. So these are the HOMO and LUMO distribution of the molecules. In both the molecules, the LUMO were concentrated on the benzotriethylene core, whereas in BQA molecule, the HOMO was localized only on one of the terminal phenyl rings. These molecules, since we could achieve the liquid crystallinity, we expected them to show good charge mobility as well. And for whole mobility study, we use the ITU and T-dot PSS as the anode, and mobility study, the whole mobility was expected to be in the order of 10 to the power minus 2, and the electron mobility was in the order of 10 to the power minus 3. And for BQA molecule, the whole mobility, the electron mobility was found to be in the order of 10 to the power minus 2. However, the whole mobility was not extractable due to inconsistency in the J versus V curve. So this probably arises from high temperature required for thermal annealing. So in conclusion, we could synthesize two noble symmetrical molecules with benzo diphenyl core with different connectivity. So this work demonstrates that polyaromatic core can be made solution processable, and they can even exhibit room temperature columnar phase. So BQB molecule was found to have columnar rectangular surface from 178 to room temperature, and BQA had a columnar hexagonal surface, and because of the amide, there was intermolecular hydrogen bonding. Because of this, the surface range was quite wide. So, and in conclusion, this BQE, it had an exceptional and bipolar conductive mobility with whole mobility in the order of 10 to the power minus 2 and electron in the order of 10 to the power minus 3. And BQA had the electron mobility in the order of 10 to the power minus 2. So, as you can see, again from pyroxenophenoxylene to benzotriethylene, the mobility again further increased. And coming to the last chapter, which is the effect of introducing 1,3,4 oxidizer connectivity on the surface and phenoxylene-based derivatives. So, as in the first work, that is the second chapter, we could obtain the surface, we could obtain the thermal surface, but with a very narrow surface range. So here we introduce our phenoxylene moiety and so these are some of the phenoxylene derivatives, oxidizer phenoxylene derivatives over the where the substitution of electron withdrawing groups on the phenyl ring, which is directly attached to the oxidizer group, resulted in the formation of hexagonal columnar mesophytes. And previous work from our lab, where different substances were used, and the one with tri-decyloxyl chains was found to have high mesophytes range from 168 to 30 degrees Celsius. And in previous work from our group and another group, where the introduction of oxidizole and hydrazole, when connected back to each other in pyridine or benzene ring, resulted in different columnar phases. So keeping these things in mind, we have proposed for pyridine molecules, where we have the phenoxylene core and then the phenyl groups, and then the oxidizole moiety, which is connected to the phenyl rings which have alkoxy chains. Here we very similar to the second chapter, we varied the substituents at position 67 of the phenoxylene core, where we have the unsubstituted, semi-substituted, and the fluorine and the direct alkoxy substituted. So this is the synthesis of the oxidizole derivatives. So starting from Williamson synthesis, alkylation of this gallate ester, we formed the alkyl dilated product, and then from here we form this hydrazide by reaction with the hydrazine, and then the hydrazide molecule is reacted with the acid chloride, which was synthesized by this synthetic route to obtain this diketo, which has di-acyl linkage. And this diketo was coupled with different diamides to give rise to the quinoxidine derivatives, which have di-acyl linkage. None of these were found to have liquid crystallinity, though I have not shown it here. Further, on cyclizing the diacyl linkage to obtain oxidizole, we obtain 4 target molecules. Coming to the mesophase characterization again, the unsubstituted and the fluorine substituted did not show any clear mesophase structure in POM, but in case of cyno-substituted, these structures were observed, and from DSC we can see the transition from one crystalline state to another state and then to isotropic, and then in Kuhn curve we can see the transition from isotropic state to mesophase state, and from XRD at 28 degree we obtain this mirror indices which correspond to the rectangular columnar rectangular mesophase with 36.8 and 34.3 with the diameter and binding distance of 3.8. And this the number, the Z value here, that is the number of molecules per unit cell was found to be 2. So because of the shape of the molecule, the two molecules form one disc. Coming to the dialkoxy substituted, here these pure textures were observed. And from the DSC, the transition from the mesophase to isotropic observed at 111, and isotropic to in the Kuhn curve, isotropic to the mesophase was observed at 103. And from XRD, it was confirmed to be columnar hexagonal mesophase with 35.6 angstrom and binding distance of 4.3 angstrom. So out of these 4 derivatives, 2 derivatives, that is QOCN and QOR, were from the liquid crystalline behavior, and from PGA we can see that all the compounds are stable. And this is the photophysical behavior of the compound. In solution state, all the derivatives showed similar absorption cycle, but in the solid state, the derivatives showed either blue shift or red shift, suggesting the formation of aggregates. And from the again, just like observed in the second chapter, the cyno-substituted has a reduced band gap value. And from cyclic voltammetric study, we have calculated the HOMO and the LUMO, and from the CV, the HOMO value obtained for cyno-substituted was found to be slightly higher than those of other derivatives. And these are the LUMO and HOMO distribution of the PO derivatives. Here, for all the derivatives except QOCN, the HOMO and the LUMO distributions were similar. But for QOCN, there was like localization of the HOMO. So here we can see that we are coming to the characterization of the PO derivatives. We can see that compared to the chapter 2, where we had ester linkage instead of oxidizing molecule, the introduction of compared to chapter 2, where we had ester linkage, the incorporation of this oxidizole induces liquid crystalline character. And if you can remember, in case of QE, the ester linkage with cyno-substituted, it was receiving texture. But here we could achieve columnar rectangular mesophase, and also for the dialkoxy substituted, the mesophase range increased. And here in the quinoxidine derivative with ester linkage, the mesophase range was very close to room temperature. Here the range increased from 0.3 to room temperature. So this demonstrates the effect of the substance at position 6 and 7 closely, and the effect of the quinoxidine oxidizole moiety in reducing the crystalline behavior. So overall, the first chapter was general introduction of liquid crystal, and in the second chapter we had chosen quinoxidine phenoxylin core to exhibit AIE and lipid crystal in the same molecule, and the mesophagus which was less, and the core mobility was found to be less in the order of 24-6. But when we come to chapter 3, the mesophagus was quite stable from 94 to room temperature, and also the core mobility increased to the order of 10⁻⁴. And in case of chapter 4, we had introduced a Viva core, and we could synthesize the two novel molecules based on benzophenoxylin, and found that the increase in core and the introduction of the linkages resulted in wide mesophagus width, and the amide derivative having the wider mesophagus range, and the core mobility and electron mobility was found to be high for BQE molecule, the aspirate derivative, and for BQA molecule, the electron mobility was found to be lower than 10.2. So, and in the fifth chapter, we had come back to the phenoxylin core and introduced oxidizing molecule to increase the mesophagus range. So, we could not study the charge mobility study here, but however, introduction of the oxidizing molecule proved that it resulted in lipid crystalline behavior, and also the mesophagus range increased for the case of diazoxy substitute. So for future outlook, so the pyrazinophenoxylin derivative was found to have core mobility in the order of 10⁻⁴. So the design of this derivative can be improved maybe by replacing the SO linkage by more rigid linkage. And for the benzophenoxylin core, it was the BQE was ambipolar with both core and electron mobility, and BQA was only showing electron mobility. For BQA, only the electron mobility will be extracted. So for BQA molecule, maybe something can be done to bring down the clearing point of the amide derivative, so that there will be no difficulty in thermal annealing, and the core mobility can be extracted. And charge carrier mobility measurement of the phenoxylin oxidizing molecule derivatives are being carried out right now. So these are the work that will be published. One is accepted, one is published, one is accepted, and others are yet to be published. So I would like to thank my thesis supervisor, Professor A.S. Kumar, for providing me the resources and also guidance all throughout my PhD, and also my doctoral committee members who have been there repeatedly. My doctoral committee chairman, that is Professor Mamilani, and then Professor Bhubaneswar Mandal, and Dr. Krishna Bhava, and also my Ghosh committee members, Professor Aditya Kandasya, and also Professor Ajay Kumar, and also my thesis examiners, Professor Subrata Ghosh, and Professor Kwan Lee, and also Professor Narendra Pratap Singh for mobility studies, and Dr. D.S. Shankar Rao, and Dr. Sandeep Kumar for XRD analysis, and CIF for instrumental facilities, and department and faculty and staff of chemistry department, IIT-Guwahati, and financial support. I would like to acknowledge the financial aid that I got from CSIR and also IIT-Guwahati. And last but not least, I would like to thank all my lab mates, friends, and family. Thank you for
Mr. Ghosh, can you hear us? So,
Yes.
So I think you can ask the questions now.
Okay. Neichoihoi, how do you pronounce your name?
Neichoihoi. Neichoihoi.
Okay. And so thank you for a very detailed presentation and a lot of work. Please. clearly reflecting from the presentation, also from your thesis. So I don't have any questions. I have two queries initially. Have you addressed, was there any comment from the foreign reviewer?
No, sir.
No comment.
There is no comment.
No comment.
Okay, fine. And then those one or two structural corrections that you have done, right?
Yes, sir.
On NMR?
Yes, sir. Those are
Yeah.
corrected.
Okay, so fine. Thank you very much. So now I have just two small questions. One is on slide 13. We go there. So for the three molecules to solve.
PowerPoint, yes. Yes.
No, not 30, 13. Okay, and so anyway, I think the previous slide where you showed for your chapter all the 6 or 5 molecules, and 3 were in the first row and then 4 were in the second row, something like that. On the slide. Yes, correct. So I have a question here for the first 3 molecule. I see that you have unsubstituted carbocycle in the first one. Then you have a dicyno. Then you have a dipro, right? And then the second series you have all the interlinkages with the long alkyl chains.
Yes, sir.
So the point is where you have only electron withdrawing groups, and if you bring there a small alkyl electron donating functional linkage, how the property will change? Did you study that instead of a very long alkyl chain one?
So which property? Yes, sir. Actually, only for the QER1 molecule, it was found to be
One molecular property.
only QER1. Whereas the QER2, 3, and 4 did not show liquid crystallinity. QER3 was found to be glassy, and QER2 and 4 were found to be crystalline.
So you think that they will lose property, but even QER1, QER2 and 3, all of them are alkyl chains, right?
Yes, sir.
So you think that if we go back, I mean, if you reduce the alkyl chain link, it will lose its other overall property, right?
The other property, as in you mean the liquid crystalline behavior?
Definitely you have studied its whole mobility, right?
Yes, sir.
And then how it will affect the whole mobility? Will it affect?
I don't think much, sir, but the alkyl chain bring about the fluidity. So the alkyl chains are required to bring about the liquid crystalline. So even non-liquid crystalline molecule can be analyzed for mobility studies.
Correct. There are many non-liquid crystalline molecules which are used there. good transporter, or meaning that they have good mobility, right? So in that, as if we go to, in continuation of this particular point, we go to slide 34. Yes. So here, though you said that the mobility is not very good, and that was one reason that you changed your structural design, and then you moved to another different kind of code, and then you develop the molecules in the next chapter, right?
Yes.
Yeah. So that's okay. So can you, so this is a device, these are the results, so what we can see from after fabricating the device. So this is the device outcome. Now, can you explain how this molecule is acting as, or how molecule is behaving good in terms of the whole mobility? Can you correlate the whole mobility with the structural feature?
So this QER1 molecule, it forms columnar hexagonal surface. So the molecule stack one above another to form columns, which again rearrange to form columnar hexagonal surface. So because of the formation of the column, there is a one-dimensional pathway that is being created, which helps in the mobility.
So that how does it help? That's what I'm asking. How does it help in mobility?
So there is a formation of one-dimensional pathway. So the flow of the whole mobility is, I don't know exactly how it works, but it has to do with the formation of one-dimensional column, directional pathway.
Yeah. So what are the molecules should have so that certain type of properties go to maybe your formation of the one-dimensional column is enhancing that. But it will be good if you just take a look later and see how the molecule, how the structure of the molecule is actually. You saw something on the slide, wait.
Which slide, sir?
558.
Yes, sir.
Yeah. So these are quite it's really very functional. Almost like it is the molecule is having dendrimer type structure, right? The code and then this and all this. So this is very quite bulky molecule. Now, as for every molecule, we have studied its whole mobility, and most of the cases I see. So that means your target, and the final goal is to use this molecule for device applications.
Yes.
Am I correct?
Yes.
So first of all, I have two questions. One question is like when the whole mobility was started, how it was processed? Which technique was used to process it?
Sir, SCLC, that is space carrier limited current method was used.
Am I correct? SCLC is a theoretical calculation. These are experimentally measured whole mobility, right?
No, sir. Yes, sir. Yes.
So what was the substrate? By forming a film or what? How the substrate was made?
Yes, sir. I think by forming a film.
Or it will take because then it will be good.
So this was the device fabrication. ITO with P.PSS. In case of air mobility study, ITO with P.PSS was used as the aero, and for the cathode, gold was used. And the compound is sandwiched between the anode and the cathode.
Yeah.
So I think the compound is deposited on the anode, surface of anode.
No, you say that it is sandwich, but anyway, whether it is deposited on the anode or cathode, how it was deposited? Was it deposited through a solution process? Was it deposited from a evaporation process? How it was deposited?
Sir, I'm not sure about that.
Or any other process which was followed to make this?
Sir, I think it is solution processed. The solution is
So you didn't check with them which process they were following, right?
but sir, the main purpose of studying making liquid crystalline molecule is to make them solution processable. So I think it makes sense to say that it was solution processed.
Okay, so assuming that these devices were made using a solution process, and so I have two connected questions. One is like, how about the solubility of these molecules? Like, what are the solvents that they are generally soluble?
Sir, the PQE molecule, it is very well soluble. Like in most of the organic solvent, it is soluble. And for the amide derivative also, it is soluble, but the solubility was lesser.
Instrument you have taken NMR.
Yes,
So,
sir.
do you think that?
Sir, the amide derivative was also soluble.
So do you think that
Yes, sir.
you're looking at issues of thermal stability, but I see like that these molecules are thermally quite stable.
Yes, sir.
So, do you think that these molecules, if they are processed through an evaporation technique, if the solution process, they are good, of course, cost effective and everything, but still the device performance of the evaporation technique is much better than the solution process one. So, do you think these molecules can be processed through thermal evaporation, or they will decompose?
Sir, in that case, I'm not sure about how the molecules will align. So I'm not sure. In case of if it is, I'm not sure, sir.
Okay. So you are saying that if it is thermal, even if the molecule survives at a temperature during evolution or thermal deposition, if the alignment is not proper, then the molecule may not show, or the film may not show to mobility, right?
Yes, sir.
Okay. So now question is, okay, whole mobility is done, everything is done, and they are showing good whole mobility. So what's the next? What devices can be made? We have checked. Now further, what will be the final application?
Sir, since they are for liquid crystalline molecule, the advantage is that they can be used for flexible devices, which inorganic semiconductors may not give. So they can be used for flexible devices where semiconductor, like it works on the basis of semiconductor.
So that is yet to be tested, right?
Yes, sir.
Okay, thank you very much. Professor Arshad, I'm done. I don't have any other questions, so thank you.
Thank you also for the evaluation. And I'll ask other committee members and any questions.
It's a good presentation and good work. So I have a couple of questions and go to slide number 27. Where you show the fluorescence. See, when I see that you have used different concepts like 10%, 20%, 30%, right? 30% is going down and crystalline jet again going on. And I have observed that in other articles. Can you go to the next slide? Sometimes it's not this one. Previously. Yeah, some places I have seen that happen. Do we know?
They form aggregates, like explain. Some aggregates are favorable, some aggregates are so pencil, some aggregates emission aggregation in this emission.
Yes. And what's the application of this?
So usually viscotic molecules, they stack one above another to form column. So when they are stacking, it is accompanied by decrease in emission intensity or aggregation cost quenching. So here in this chapter we try to design a molecule which can show liquid crystallinity, and also this is an effort to see if we can come up with
It's good.
Where it can be applicable, having the aggregation in this emission and also columnar structure, it can be applicable. Organic light emitting layers.
Okay, I have few minor questions. Go to 23. Okay, let me first make that comment that very good work. You don't have full screen because you have to go to other slides also. So good work. I mean, you have shown like how small design changes can really affect the overall performance. That's what you have shown. In many cases, it doesn't really change much, but in many cases it does. So this is done. So here, this is 23. So only you said TVR1, no?
yes.
That was the one. Okay. I wrote it down because by this time I didn't have much idea. When you weren't I found that idea. So QER1 was it whole 10 OCS or 10 of them.
Yes.
3, 3, 3 and then this side 2.
Yes.
Yeah.
Total 8 chain.
3, 8, not 10, 8. Yeah, I got it. It was 8. So it is very surprising that for me that going from 1 to 2, 1 to 2 is a sudden change. I mean, is this like how many times do you do the experiments when you do? These experiments when you do liquid crystalline property characterization analysis mesophase like you were saying. So how many times do you do really to check? Going from QER1 to QER2, the change is like OCS3 or the longer chain of OCS3.
6 chains will be. You see, here it is 8 chains.
Yeah, so the change is like in that benzene one O is taken out and here also one O is taken out. So that is making all the changes. Right? That are like how do you you do experiments more than once to verify all that?
So after synthesizing and purification of the molecules, each molecule is checked separately. So first we check by polarizing optical microscope, and we heat it to its isotopic temperature, and then cool it slowly at a slow rate, and observe under the microscope if we find the formation of birefringence and texture. So if we find that is a preliminary study set. So if it forms texture, we check for the shareability of the compound. So liquid crystalline molecules are known to show shareability.
Yeah. So what I was asking is, do you do that experiment twice to verify?
Yes.
Yes. That's the answer. So
And also DSC, how many times DSC you do? How many cycles of DSC you do?
Yes, sir. Sir, after PO1 study, we check the DSC. So in DSC, we can see the phase transition temperature and DSC we do 2 cycles, and the graph that we plot, that is the first cooling and the second cooling.
Okay, we want to look at the board study. Okay, so here you have CN and you have F.
Yes.
So, in the homopat of CN and F, the difference that is surprising.
So actually, in case of phenoxylin derivatives with ester alkanes, the HOMO was localized mainly on the phenyl, terminal phenyl. And even in the case of the rare oxidizer molecules in proteins, it showed similar HOMO distribution. And this the QE, the H and the fluorine substituted fluorine, even though it's an electron withdrawing group, maybe because of the small size, it does not have that impact.
Yeah, so that's what is very surprising. It's not HOMO should not really show that of difference, but then it shows. Yes, that we already explained as far as also. So, regarding this whole mobility, so here it is 0.2 10 to the power minus 5. The following chapter was 5 into 10 to the power minus 4, which is like 0.5 into 10 to the minus 3. That is a huge change. Huge change. So what is the good number for the whole mobility?
So the greater than
Just
that.
a general level, what is a good number?
Sir, for liquid crystalline molecules, 10 to the power minus 2 or minus 3 is a good.
Okay, we are already having in the next chapter, so it's to the minus 3.
Yes. Whole mobility 10 to the power minus 2 and electron mobility 10 to the power minus 3.
37. Here you mentioned that 2 and 3, they don't show, no? 1 and 4.
Yes.
And you mentioned that they could be because of that OCH3 type of alkoxy chains, not because of thiophene.
Sir, compound 2 and 3, they were not liquid crystalline.
That's not, so they are not not because of thiophene, you mean you are mentioning only that alkoxy chains, but thiophenes are also there. So thiophenes, like, have there been situations where thiophene containing systems like these, they are liquid crystals?
I think so.
Okay, so 46. The differences are like very, very minor,
Yes, sir.
which is expected. That's what I expected here also and there also, in the first picture also. The differences are should not be that much. Like here. Don't have much. And go to 69. So here you have put fluorine. I think somewhere else also you had fluorine atom.
Yes, sir.
So in the previous chapter also you had fluorine be there. So why do you put CN and fluorine? What sort of a difference do you expect, and why is it, in this case there is a difference? Okay, fluorine doesn't and that is. So why did you expect that in the beginning? From the literature, or you had some idea? Okay.
Sir, from the literature, phenoxylin-based derivatives where the electron withdrawing substitution is done at position 6 and 7 and resulted in liquid crystalline behavior. But in that case, it was it was cyclized at this position. and also in the ester linkage containing compound, the cyano and fluorine substituted were found to be PLC in nature. So even for the oxidizing molecule containing oxygen derivatives, we wanted to see if the oxidizing moiety can induce lipocrystalline removal.
Which one is more relevant?
Cyano.
77. I forgot what I was supposed to ask you. Doesn't matter. Go on to 79 last. Years before that. Before that. Yes. Year also. Yeah, okay. I'm done. It can happen. Okay, I'm done.
Okay, so you have put all the saturated alkyls. They affect to incorporate unsaturated.
Sir, this alkyl, the saturated alkyl chain, they increase the fluidity of the molecule. Like it becomes flexible and more fluidic. So that helps in stabilizing the surface.
But you will attempt to include the unsaturation.
Sir, the unsaturated is not that flexible, so we usually work with
Especially the three positions because the unsaturated. So, these are maybe telling these unsaturated oils. They are having lower weight. So, why it is because they are completely unorganized. You will have this linkage in class or all these things will happen. This should be not many people attempted here. Unsaturated. The other problem is that they will polymerize during the synthesis or that maybe when heating also there. During heating also thermal polymerization or you need to explain all these topics. Students, any questions? So, Professor Ghosh, so any other questions? Professor Ghosh? Professor Ghosh, can you hear us? Hello? Hello?
You can stop sharing.
Yeah.
Firefox.
Using Firefox or Hello? Hello, can you hear us? Oh, you can hear us? Okay. So, I think so now all the questions are done. So, if you have any other questions, okay.
Stop sharing.
Okay. If you are fine with the Viva and all, then I think you can formally announce the result.
Microphone.
Oh, your microphone is not here.
It's not clear.
Hello? Hello?
You can put the phone on speaker.
Okay. Yeah, I have put on speaker. So, so you can announce the result and congratulate her.
Yes. So what I'm saying is your report, we are all here only
send it. Yeah. Yeah, sure. Okay, all the best. Congratulations.
Okay, congratulations.
So I will send you the forms, okay? I will send you the forms. Yeah, I will send you the forms. I will send you the other forms. You can sign it and send it. Thank you so much for spending your time in evaluation as well as yeah. We will try to take it for just wait for some time. We will take it for some time.
Cái này bùi đàn ăn lâu pi e i mà lâu à con hết sân cả luôn nang zal a hi pa kai ka ki pa ka gel pa lâu san gay này bùi e pa kai nang zal a hi pa kai ka ki pa nang zal a hi hi chan kan hun the na phat na ho hi ka gel zi te a lo pi dan tim thu a se zo hi lo o pa kai I pi ham ka bolu hin ho mo so na ding hat na kan nei poi hi zong le pa kai phat na zalin ma nei pui lung pa kai na hat na zalin nang zal a hi pa kai ka ki pa nang zal a hi chan kan hun the say zo